All right, guys. On Thursday, tomorrow, the schedule is as is. Like, we're still going to continue doing business. Should be pretty easy because none of the juniors are here. They're going to be testing SAT. We're not displaced. We're in this room, so good. And then on Thursday, I'm thinking the day right before Friday. I'm thinking Thursday, I'm going to pass back your free response questions. We're going to tell you, like what you did, what you didn't do, all that good stuff. All right, volumes of solids of revolution. We're just going to go over the basic ones. So we're either going to rotate or on the x-axis or on the y-axis. So here we go. You guys ready? So the region between the graph y equals 2 plus x cosine x and the x-axis over the interval negative 2 to 2 is revolved about the x-axis to generate a solid. Find the volume of the solid. So those of you that love art, you're going to love this. So what I'm going to do, you see the x-axis? Pretend that's like a spindle. I am rotating that. When you rotate it, it comes out of the board or out of the paper, and then, in a circular motion, and then it goes back inward, and then goes behind the paper. Can you guys kind of see that? So let's first start by reflecting the image. So I'm going to start putting points. Let me see if I can. I'm just measuring here with my little finger. And let's see, point. That looks like a little more than 2. So, and then all right, so let's see. I'm going to see if I can reflect across the x-axis here. So check it out. When you rotate it, let's see if I can make it look three-dimensional.
No way, Todd. You can't help me with this. I love it. It doesn't let it go fit.
Does that look three-dimensional to you?
Oh, yeah.
I tried to make it look three-dimensional. So notice the curvature of this right here. All right, what does this look like? Yeah, a vase. And if we remember, we got to find a common cross section. I actually did a 3D model of this. So let me show you that 3D model that I did a little earlier. So here's that curve from negative 2 to 2. And I'm going to click on See Surface. And there it is. And check it out. Let me spin it. Let's see if I can. Yeah. Look at that.
Whoa.
Cool, right?
Okay, yeah, I see the base. I'm seeing it and seeing like Big Bang Theory. I see a doorknob. I don't know.
Yeah, it could also be like a doorknob, the way it looks. But cool though, right? Yeah, if you don't know the dimensions, it could be a doorknob, it could be a vase. It just depends. So maybe they exaggerated the image a little bit, but that's pretty cool. And maybe one day we'll do cool stuff like this soon. Or I mean, we're doing cool stuff all the time. Yeah, we're doing it now. All right, here it is. You guys ready? Pretend this is a cake. I don't know. I mean, obviously it's already a vase, right? I need a common cross section. So here it is. If I cut it like this, what is the shape of this common cross section? No, look at that. It's a circle. Do you see that?
Yeah.
And it doesn't matter where you cut it. Look, if I cut it right here, it's still a circle, a disc. A disc is what they call it in math terms, but it's a circle. Do you guys see that? So here it is. I'm going to find the volume. How do I find it? I'm going to go volume equals. And what is the area of a circle? Pi r squared. So pi on the outside, integral. From what to what? Negative 2 to 2. And I need my radius, pi r squared. Remember, all I'm doing is integrating the cross-sectional areas, and I'm adding an infinite amount. So what is my radius? The distance from the x-axis to this curve. What is that curve? Yep. Parenthesis, 2 plus x cosine of x. Close it. Put a what on it? Squared, and put a dx. That is my area cross section, and there it is. I'm integrating. Chav, why isn't the pi in there? Because it's a constant and it's a product, pi times r squared, so you can put the pi on the outside. Does that make sense, guys? All right, you take your calculator. So let's take our calculator, and I'm going to go math 9, negative 2. Let's see if it's a pretty number. Parenthesis 2 plus x cosine x. 2 plus x cosine x. Oh, there's a reason why I didn't do that. Let me see if it comes out pretty or not. You can, but no, it doesn't come out pretty. So I am going to put the pi. Yeah. All right, let me put the pi back in there. Math 9, negative 2. I guess 6.88. Maybe it would have 88 forever. No, probably not. And then parenthesis 2 plus x cosine x close squared x. And I guess I could have also taken that 6.688 and multiplied by 3.14. And there it is, 15.42. Let's see, if I would have taken this guy, multiplied by pi. Yeah, I would have gotten the same thing anyways. There it is, pi r squared. I don't see any mistakes. 2x cosine x. Yeah, I think we're good. And did everyone get that, guys?
Yeah.
All right. What is this volume? 52.428. It doesn't have units, so you can leave it like that. And that's it. Cool or not cool? Yeah, pretty much. No, we're still rotating around the x or y axis. It doesn't really get hard if you think about the concept, but we'll figure it out. All right, let's do this freehand. The region in the first quadrant enclosed by the y-axis, the graphs of y equals cosine x and y equals sine x, it revolve about the x-axis to form a solid. Find its volume. No calculator. Okay, you guys ready? All right, so here we go. Let's just first see if we can draw cosine x and sine x where they intersect. Let's find the region first, what they're talking about. So here's my grid, and let's see. Cosine x looks like this. In a little bit, I'm going to delete. And sine x looks like that. So they're talking about, let's see, the region of the first quadrant enclosed by the y-axis, the graphs of cosine and sine, draw about the x-axis to form a solid. They're talking about this region right here. So I'm going to cut it like that. Cool or not cool? And I'm rotating this about what axis? The x. So I'm going to put a little whirly thingy right there, my spindle. So it's going to look like, let's see. It's going to look like, point here, and it's going to look, and then let me stretch this guy. All I'm doing is trying to reflect. Let's see, that distance, that's my cosine. There it is. I think I did a good job, or an okay job, not the best. You really don't have this part. There it is. That's how it really looks. And there's my rotation. You have like an open funnel right here. You can probably put your hand through it. And the other part is the shaded region. So there's your solid. You guys kind of see that? And when you cut it, well, almost like an eyeball, because this is empty there. When you slice it, how am I going to slice it? I'm going to slice it like this. When you slice it, this is a specific shape. Yeah, that's a disc, but be careful. Look what I have in the middle. No, well, it's empty in the middle. So, yeah, let me. So you have, look, this is empty right here. This is empty right here. The shape, this is the solid part. You guys see that? This is the solid part. So right here, all this kind of open funnel type of thing is blank. So this is called something very specific in math. You've seen it every day. It's a shape that you guys use all the time in robotics. What is that shape? Here's a slice. Let's see. A washer. A washer. This is a washer. This is blank. Everything else is filled in. Does that make sense? How do I find area of a washer? I'm going to call this big R. So I'm going to put capital R. And I'm going to call this little r. So area of the big circle is pi big R squared minus, and then area of the little circle is pi little r squared. And that's how you would find the area of this washer. Does that make sense? If you factor out a pi, look what you have. Big R squared minus little r squared. And you always have washers on the entire interval, except for the two extreme values, right at way over here, which we got to find out where they intersect. At this moment right here, this specific moment, you have you have nothing. And then right at 0, you have a disk for a moment. Does that make sense, guys? All right, but everywhere else, wherever you slice it, forever and ever, you always have washers on this. All right, so here's what we got to do. And we all took pre-cal, so we should all be able to figure this out. Where is cosine x equal to sine x? When x equals, that's the y value. At what x, where does cosine x equal sine x? Give me a radian. 45 degrees, I need it in radian. Pi over 4. So this is pi over 4 right here. Cool or not cool? So here we go. If I want the volume of this, volume equals pi on the outside, integral from 0 all the way to pi over 4, parenthesis, and I'm going to write, let's see, what curve is on top? This curve, well, okay. Yeah, sorry, I don't want you guys to be a robot. I need big R. The distance from the x-axis all the way to that curve. That curve is, bless you, cosine. So I'm going to write cosine squared x. Does everyone know why I'm writing cosine squared x? Because it's big R squared. Minus, and then the little r is the distance from the x-axis to the sky blue or the little curve. The sine curve, yeah, not the little curve. Sine squared x. Close it, dx. Yeah, it is. It's a formula. Do you remember the formula for cosine squared minus sine squared? All right, side note. No, cosine squared plus sine squared is 1. So go up here. No, I'm not going to gaslight anyone. Do you remember that cosine A plus B was cosine A cosine B minus sine A sine B? That's why we took pre-cal. You think we just... So if you turn one of those into A plus A, so cosine 2A, then this would be cosine A minus sine A, which is what we want, because that's cosine squared A minus sine squared A. So now you know that cosine squared A minus sine squared A is nothing more than cosine 2A. So I'm going to come back, and I'm going to replace cosine squared x minus sine squared x with just what? Yep. Cosine 2x. And I can do the antiderivative of that pretty easily. Right? At least I hope. What's the antiderivative of cosine 2x? So first take the antiderivative of cosine, which is what? Sine, keep the argument 2x. Now if I would have done chain rule, it would have been times 2. But I don't have a 2 here, so I got to multiply it by 1/2. And I'm evaluating this from 0. Oh, there's still a pi on the outside. So don't forget your pi. Let me put the equal sign and pi here. And I'm evaluating this from 0 to pi over 4. I recommend you take that half out. You can leave it in if you want, but I recommend you take it out. Pi over 2, bracket, sine, parenthesis, 2 times pi over 4 turns to pi over 2, minus sine of 0. Are we still okay? What's sine of pi over 2, guys? I don't know.
Oh,
That's,
wait.
sine of pi over 2 is
Sorry.
1. No, it's okay. It's okay. It's okay. Your brains are going 100 miles an hour. I get it. Yeah, I know. I know you would have. All right, guys. I think we might be lucky that we're in Cal AB. In BC, they would expect you to. Your professor's going to want you to know trigonometric tricks. So when you get to the university, make sure that you know cosine squared plus sine squared equals 1, and then all the little trig deals. Okay. Cool or not cool? Oh yeah, it's 90 degrees outside, guys. So yeah, 80. It's 88 degrees. Yeah. All right, here we go. Here we go. Question 3, and we're gonna go slow. The region enclosed by the y-axis, the line y equals 2, and the curve y equals square root of x is revolved about the y-axis. So let's do this together, guys. So let's see. I'm going to do a sketch. Here's my sketch. Region enclosed by the line y equals 2. So here's y equals 2. There's y equals 2. The curve y equals square root of x. So here's y equals square root of x. Let's see, what else am I enclosed with? The region enclosed by the y-axis. Okay, so this is the region they're talking about. They're talking about this region right here. Cool or not cool? Cool. So make sure you're able to tell what region, guys. All right. And I'm rotating about what axis? The y. So now if I rotate it about the y, look how it's going to look. It's going to look like this. It almost looks like a cone. It's not quite. I bet you the volume of a cone is going to be very similar to this one. The volume of the solid is given by the definite integral pi y squared dy. Okay, let's find out. All right, here we go. I'm going to go ahead and do my little... All right. Yeah, I didn't do a good... Let me draw it better, guys, because this drawing sucks. Oh, well, I wasn't satisfied. No, you leave your drawing alone if you did it okay.
No.
All right, here we go. Here we go, guys. Check it out. Check it out. Check it out. Check it out. We're doing a rotation. Guys, focus, because we're going to have issues here. We're rotating with the y-axis. I want you to see the slice. This slice is not a dx. It is a dy. Do we notice that? That's a dy. We need to have our integral in terms of y, not in terms of x. So before I even start, I'm saying, okay, so I'm going to write square squared. X equals the square root of, x equals y squared. Cool or not cool? All right, so here we go. Remember that this value way up here was 2. So how do I get this volume? Pi on the outside. So here we go. Volume equals pi on the outside. Because it's pi r squared. It's a disk. Integral. What's the lowest y value? No, 0. What's the highest y value? 2. Now the radius is the distance from the y-axis to that curve. What is that curve? Y squared. So I'm going to write y squared, and then what do I do to that? I got to square it again. dy. Do you guys see that? So to get the volume for this, it's pi integral 0 to 2 of y to the 4th dy. So is that what they have? No. So this one is going to be false. How do we feel? All right. Here we go. Focus, guys. Focus, because we're gonna be done pretty quickly here. Let R be the region in the first quadrant bounded by the graph 8 minus x to the 3/2, the x-axis and the y-axis. Which of the following gives the best approximation of the volume of the solid generated when R is revolved about the x-axis? Okay, here we go. I have an idea how this graph looks. I have not typed it anywhere, but because of the x to the 3/2, I have an idea. Shav, what are you talking about? I see that my y-intercept is 8. Do you guys see that? And here's what I see. 8 minus x to the 3 halves. When does this equal 0? Well, whenever x to the 3 halves equals 8. And I know, look, notice that it says to the 3 and then the square root. I believe 2 to the 3rd power. Let's see. Well, let's just do it. I'm going to raise this to the 2/3, and I'm going to raise this to the 2/3. The cube root of 8 is 2, and 2 squared is 4. So I see a 4 here. So it probably looks something like that. Does everyone see how I got that 4 there? Okay. I hope that you can do stuff like that without a calculator as well. Where am I rotating this? About what axis? The X. So do a little spindle there. Bless you, bless you, bless you, bless you. So here we go. Put a point. And it kind of looks like a dome, but on the side. Look at this. Here is my curvature to indicate that I'm rotating. And it kind of looks like if you think of a paperweight with a little round in shape. Almost like a what?
Like the top of a pie.
Oh yeah, kind of like the top of a pie.
It's like a beautiful, like animated pie.
Right.
Yeah.
Here we go. Here we go, guys. When I take a slice, there's my slice. What is that shape? A circle. Everywhere you cut, it's a circle. Do you guys see that?
Yeah.
Volume equals integral, or pi on the outside, pi r squared. That's the area of a circle. Integral from what to what? 0 to 4. And what is my radius? The distance from the x-axis to this curve. And that curve is? Close it, put a square on it, dx. This you need a calculator. Take your calculator. Let's see. Pi, math, 9, 0, I already forgot. 0 to what? 4? And then, I know I usually put it in y1, but parenthesis 8 minus x to the what? 3 over 2. And then I'm going to get out of there, and I'm going to put a square on it. And then get out of there, x, push enter. 361.911. 361.911. Oh.
I love that song. You should listen to that song.
Oh, okay. I will. Oh, I'll let YouTube recommend it to me, since it's always listening to me.
Yep.
I bet you it's going to come up now. All right. Oh. All right, guys, check it out. I want you to notice that the answer choices have a pi in them. So relax. That just means don't include the pi. At the very end, we put a pi. So let R be the region enclosed by y equals x squared. Does everyone know how y equals x squared looks like?
Yes.
It's a parabola, right? So here's y equals x squared. I'm exaggerating it. The line x equals 4. So I'm going to call x equals 4 to be this line right here. It's kind of, yeah, there we go. And the x-axis. Oh, okay, so they're talking about this region here. Then they should have told me the first quadrant. They didn't tell me that. Okay. It's okay. It's okay, guys. There we go. So there it is. Which of the following is the best approximation of the volume solid generated when R is revolved about the y-axis? Oh, no wonder. So we still had the parabola anyways, but it doesn't matter. We're good. It's not a big deal, guys. So, yeah, kind of like an hourglass. This is empty and the top is empty. Yeah, it is going to be. I accidentally erased it. It does look like, what am I rotating this about? Oh, the y-axis. So here it is. So here is my slice. I didn't do it perfect. I'm sorry, guys. So the top part is a circle. There it is. Do you kind of see it's like an acorn shape, but the hollow part is an acorn shape. The hollow part is an acorn shape. Here is my slice. Notice that the slice, is it a dx or a dy? It's a dy. So I need to have my integral in terms of y. Because it's a dy. You're adding them all up. So here we go. X equals the square root of y. All I did was just, and that's all I need. All right, here we go. That's all I need because so we have a big R. So before you even start, maybe put this on the side so you don't get confused. To find the area of a washer, it's pi big R squared minus pi little r squared. I'm factoring out the pi, and you have big R squared minus little r squared. Cool or not cool? So here we go. Volume equals pi on the outside. Integral. What is the lowest y value?
Oh, 0.
0. Because we're doing dy's. My highest y value, remember, x is 4, is 16. That number way out there is 16. It's not drawn to scale. How do we know that? We plugged in x equals 4 in here, and we got the y value of 16. So that's how we know that that's way up at 16. Are we okay so far? All right. The radius is the distance from the big R. I need the big R. So I'm going to put an open parenthesis. The big R is the distance from the y-axis to way over there. And I notice that it's always what? It's always 4. So put 4 squared minus, and then the little r is the distance from the y-axis to this curve, which happens to be square root of y. And we're going to square that, dy. Cool or not cool? More than likely, the way this looks, they probably want you to do it by hand. So let's go by hand. What's up?
Would the minus square root of y squared just be 1?
Yes. Yeah, that's right. Yeah. More than likely, guys, this would be one that would do it, that you'd have to do by hand. So here we go. Pi integral 0 to 16 of, I'm going to write 16 minus y dy. Can we do the antiderivative of that pretty easily? Yeah. Volume equals pi on the outside, bracket. The antiderivative of 16 is 16y minus y squared over 2 from 0 to 16. Do I have to worry about the 0? Not in this case. Pi, bracket, 16 times 16. Ooh, what is that? 256? 256 minus 16 squared is 256 again, but when I divide it by 2, I want to say that's 128. So 256 minus 128 is 128 with a pi on it. So there it is, 128 with a pi on it. How do we feel?
Good.
Okay. All right, let's see this one. Let R be the region enclosed by the graph y equals e to the negative x, y equals e to the x, and x equals 1. Oh, okay, I like it. I like it. Which of the following is the volume of the solid generated when R is revolved about the x-axis? Guys, do you guys know how these functions look?
Even the x, isn't it like, yeah.
Yeah. Here, look, I'm giving it to you guys. E to the negative x looks like this. Chav, how do you know that? How can you figure it out without... Remember, guys, E is a number like 2.71 or whatever. So whenever you raise it to the negative exponent, all that does is like, okay, Chav, I don't know what you're telling me. Look, guys. E is a number like 2. It's not 2. It's 2.71. But if I raise it to the negative x, what does that mean? That means 1 over 2 to the x. As x gets larger, the denominator gets larger, and 1 divided by a big number is approaching 0. So as x gets larger, I'm getting closer and closer to the x-axis. Does that make sense? And what about this one? Y equals e to the x. Well, that one's like a number like 2. So do you know how this one looks? Well, as x gets larger, 2 to the power x just gets larger. So I'm growing without bounds. So that one looks like this. See? Yeah. So, guys, make sure we took all these classes, Algebra 1, Algebra 2, so we can know behaviors. So make sure that we are at least up to par with that. Okay. Let's see how this graph looks. Let's look at the region. So I have, let me draw the grid first. Here's my grid, and let's first draw e to the x, or that's e to the negative x, sorry. E to the negative x, e to the x, and x equals 1. So, boom. This is the region they want. They want this guy right here. That's the region they want, guys. Cool? That's the region they want. Ooh, I don't know if we're ready for... Yeah, no, we're ready. We're ready. I'm rotating this about what axis? The x. So when I rotate this about the x, this is right on the y-axis there. So let me see if I can draw this pretty good. And point. There it is. Beautiful. Look at this. Beautiful.
What is that?
You can put your hand through there.
That genuinely hurts. What? I don't know how to get.
Kind of like a lamp. Yeah, the outpost, the outside of it.
I see it like an ant.
But it's not, I mean, remember, the middle stuff is empty. It's the outside that is.
Okay. I see it. So, would that be like a washer?
It is a washer. It is a washer. It is a washer. Here we go. Volume equals pi on the outside. It's a washer, guys. Integral. What's my lowest x value? Those are all dx's. 0. What's my upper x value? 1, because it's going from 0 to 1. The first r, the big R, the distance from the x-axis way up there. What is that graph right there? That's y equals e to the x. So e to the x, close it, put a square on it, minus, now I need little r, x-axis to this curve right here. What curve is that one? E to the negative x, close it, put a square on it, dx. Now I'm going to look for that answer. So laws of exponents. So here it is. Volume equals pi integral 0 to 1. E to the x raised to the 2. You can just multiply them. Bless you squared. Bless you cubed. E to the negative, bless you to the fourth power. Look for that. Is that answer in there? D as in Daniela.
What? Oh, sorry guys.
You said B? It needs to have a pi. It needs to have a pi. All right, guys, I'm not adding you homework. What I'm going to beg of you is to re-look at these notes again, because tomorrow we're going to do this again, but we're going to be rotating around something that is not the x-axis or y-axis.
Y-axis.
We're going to be rotating around a different axis, like y equals 2 or y equals 5. So make sure that you got this on lock, please, because the concepts are the same. All right, take care of business, work on your corrections.